Myself, Pankaj Barman, student of Chemistry Honours, Mathabhanga College. Now, I am going to discuss about IR spectroscopy. The IR spectroscopy known as infrared spectroscopy. We know infrared belongs into our electromagnetic wavelength. If we look at the wavelength, it is a large wavelength much bigger than visible wavelength. That's why we cannot see infrared, but this infrared light can be very beneficial for understanding the structure of different chemical compounds, especially chemical groups. IR spectroscopy, also known as vibrational spectroscopy or chemical group or chemical related spectroscopy. IR spectroscopy actually helps us to find out the structure of different chemical groups that are present in a molecule. We have different techniques to find out the structure of different chemical groups. We have NMR spectroscopy, mass spectroscopy, etc. But the IR spectroscopy is not the powerful to give a data about the whole chemical compounds, but it is good enough to give data about the functional group that are associated with the target molecule. Now we know that E equal H nu equal is C by lambda, where 1 by lambda equal nu bar, and the unit of lambda is centimeter. So the unit of nu bar is centimeter inverse. So we get wavelength nu bar is directly proportional to frequency. Now we discuss wavelength in centimeter inverse, and its range 400 to 4000 centimeter inverse. We can observe here two ranges. One is 500 to 1500 centimeter inverse, and another is 1500 to 4000 centimeter inverse. 500 to 1500 centimeter inverse range is for fingerprinting region, and another is functional group region. Here all the functional groups are influenced. This range is called stressing frequencies, and another is called bending modes of vibration. The bending range of vibration has some benefit. For an example, we take 1 degree alcohol and 2 degree alcohol. The 1 degree alcohol give a peak in the range of 3300 to 3400, and 2 degree alcohol give a peak 3300 to 3400 also. So how can we determine what is 1 degree and what is 2 degree alcohol? By the bending region we can determine it. Now I discuss about some vibration modes. Here vibration modes are two types. One is bending and another is stressing. Stressing are two types. One is symmetric and another is asymmetric. For example, we take in nitro group. It has two possibility structure. In the range of 1350, it shows symmetric because in this range it shows same direction, and in 1550 range it show asymmetric stressing because in this range it show opposite direction. Now bending are two types. One is in plane and another is out of plane. In plane there are two types of bending. One is scissoring and another is rocking. For example, we take a molecule like Ab2. In the scissoring, the both B are go opposite to S other or come towards, and in rocking both the B are go same direction. Now, out plane are two types: twisting and vagging. Here, in twisting, one bee is come in front and another bee is go to the back, and in vagging, both bee comes front or go to the back. For can understand IR spectroscopy, we take formaldehyde. Suppose in the 2 Hz frequency it show stressing, and in the 4 Hz frequency it show vagging. Now in the chamber we take formaldehyde like our experimental molecule and put here IR spectroscopy source light. If we put here 1 Hz frequency light, there are no influence we can see, and whole the light are absorbed by the detector. It means 100% emission. If the detector connected with computer, we get a graph. For 1 Hz frequency we get planar line. Now we put 2 Hz frequency light. For the 2 Hz light, maximum of the light are absorbed by the molecule, and the graph should drop. Again, for the 3 Hz frequency, whole the light are absorbed by the detector and we get planar graph. For 4 Hz frequency light, the graph again should drop. So we can see here in 2 Hz and 4 Hz frequency it give peak, that means vagging and stressing occurred here. Thank you.